We have engines that can propel an aircraft at 5 times the speed of sound. New York to London in 90 minutes. That future is technologically within our grasp. So why are we still flying in aluminum tubes that take 8 hours? The problem isn't a lack of power. It's not about the engine. The barrier is invisible, fundamental, and brutally destructive. It's a wall of fire that materializes out of thin air, and it has stopped the dream of hypersonic travel for over 60 years. The secret isn't in making things go faster, but in surviving the very act of speed. To understand this wall, we have to look back at the last time we flew civilians faster than sound. The Concorde. A masterpiece of engineering. It cruised at Mach 2, over 2,000 kilometers per hour. But speed came at a cost. During flight, its elegant aluminum skin heated up to temperatures that could boil water. The nose cone alone reached 127 degrees Celsius. The entire fuselage, nearly 62 meters long, would physically stretch by almost 30 centimeters due to thermal expansion. Concorde flew on the very edge of what its materials could handle. Pushing to Mach 3 would have been catastrophic. It was a stunning achievement, but also a stark warning. The dream of supersonic passenger travel ended in 2003, not just for economic reasons, but because it showed us the boundary. A thermal limit where going faster meant courting disaster. Most of us think this heat comes from friction. The simple idea of air rubbing against the plane's skin. But this is a profound misunderstanding. The real culprit is far more violent. The true enemy is compression. Imagine a simple bicycle pump. As you pump it quickly, the barrel gets hot. You're not creating friction inside. You're rapidly compressing the air, forcing its molecules closer together, which dramatically increases their temperature. This is called adiabatic compression. Now, scale that up to 5 times the speed of sound. At Mach 5, the aircraft is moving so fast that the air molecules in front of it simply cannot get out of the way in time. They pile up in an incredibly thin, dense layer. This creates a shock wave, a boundary where air pressure and temperature skyrocket almost instantly. The temperature on the leading edge of a hypersonic vehicle can exceed 2,000 degrees Celsius. Hotter than the inside of a blast furnace. This isn't just hot air anymore. It's plasma, a fourth state of matter where electrons are stripped from their atoms. This superheated electrically charged gas is chemically reactive and will aggressively eat away at any conventional metal, melting it into slag. It's not friction. It's physics, turning the very air into a blowtorch. We learned this lesson the hard way. In the 1960s, the pinnacle of atmospheric speed was the North American X-15. On October 3, 1967, pilot Pete Knight pushed the X-15 to Mach 6.7, a record that still stands for a piloted, powered aircraft. But this triumph came with terrifying evidence of the heat barrier. The aircraft was built from a nickel-chrome alloy called Inconel X, designed to withstand extreme temperatures inside jet engines. Yet, during re-entry, parts of the X-15 surface reached over 1,200 degrees Celsius. Ground crews discovered that the heat had been so intense it had visibly melted and deformed sections of the wing and tail. The vehicle had literally started to disintegrate in flight. They had hit the wall of fire, and it nearly cost them everything. So, what does it mean if we finally conquer this barrier? It means a revolution in global connection. Companies like Boom Supersonic are taking the first cautious steps back. Their upcoming jet, the Overture, is designed to fly at Mach 1.7. It wisely stays below the most extreme temperatures, leveraging advanced carbon fiber composites that are both lighter and more heat-resistant than Concorde's aluminum. This isn't hypersonic, but it's a critical stepping stone, aiming to cut flight times in half and prove the economic and material model for a new generation of supersonic travel. This is the ground floor of a new era, rebuilding our confidence and supply chains for high-speed flight. But to go truly hypersonic, to reach Mach 5 and beyond, requires a leap into exotic materials science. This is where the real challenges lie. We need materials like ceramic matrix composites or carbon-carbon, the same stuff used for spacecraft heat shields. These materials are brittle, incredibly expensive, and difficult to manufacture. And this is where NASA's quiet revolutionary, the X-59, comes in. Its primary mission is to solve the sonic boom problem, turning it into a gentle thump. But every flight it takes at its target speed of Mach 1.4 provides invaluable data on how modern materials and coatings behave under thermal stress. The X-59 is a flying laboratory, testing the very building blocks that a future Mach 5 aircraft will depend upon. It's teaching us how to walk through fire, one meticulously recorded data point at a time. Ultimately, the journey to hypersonic flight isn't a race of engine power. It's a painstaking generational quest for materials that can withstand the laws of thermodynamics. We aren't fighting air friction. We're trying to build a vessel that can survive being wrapped in plasma. The sound barrier was broken with brute force and courage. The heat barrier will only be broken with intelligence, patience, and materials born from the crucible of a furnace. The future of flight isn't about going faster. It's about not burning up on the way. What do you think is the biggest hurdle left to solve? Let us know down below. Thanks for watching.